The valence bond theory describes molecular geometry, the same molecular geometry that was described using the VSEPR theory. So in the development of this, understand that where we're going with it is to describe the same geometries that were described in the VSEPR theory. So as you looked at the handout that I gave you on the two systems, you'll notice up here is the VSEPR theory, and is the AX2 through AX7. But down here you'll see some symbology that's a little different than in the first one. But both are describing the same, can be used to describe the same geometry of a given molecule. So that's the first thing you need to understand, that we're not doing anything really different in terms of the outcome, but how it's done is a little bit different than the VSEPR. The second thing is, in using the valence bond theory, I found it very helpful to use the VSEPR to first define the parent and then go from there into the hybridization type bond. So keep those 2 points in mind. We're still talking about the same geometries, parent geometries, and defining the geometry by the VSEPR helps us define the geometry by the valence bond theory. So, the beginning, what is the process that's going on? So, hybridization. Of valence orbitals is the issue. Now, the term hybridization means that the valence orbital is undergoing a change from what it is in the atomic state into a new geometry or configuration in the bonded state. So this is atomic orbitals change into a hybridized orbital is the essence of what I'm talking about. Now, to understand this, we're going to talk about bonding in methane. And it is an AX4 geometry and parent. So when we look at it from the VSEPR standpoint, we have a carbon bonded covalently to 4 hydrogens. And it's a tetrahedron, we know that. But when you look at carbon as the central element, and you look at its electron configuration, it has a helium core. Of course, carbon by itself, its atomic structure will be in this position with a helium core, and then you put in the orbitals by the electron configuration, which is 2s, that's full, and you have a 2 px, py, and a pz, and you have these electrons, as you recall, have to enter by parallel spin, yada yada yada, like that. Well, the structure, this is the highest principal quantum number in there, and is the valence structure right here. Now, what you need to understand in this structure, in this valence structure, is that the S and, well, actually the helium structure, the S and the p orbitals are at different energy levels. And so that's where this little diagram comes into effect in understanding what I'm talking about. In each one of these parts, the helium is down here. There's your 1s orbital down here at this level, and then you have a 2s at that level, then you have the 2p's, and then if you go on to other elements, you see how they separate, and the positions of their potential energy are different. That's one thing to look at. Okay, second thing to look at is that if you have carbon, helium core, and start out with this atomic configuration, valence configuration, what you're having to put in here is 4 S1 orbitals. So you have to get 4 of these electrons into the valence structure of carbon. Where do you put them? Well, here's the problem. Trying to put this into the present atomic configuration, you can't do it. The s orbital is full. You have 1, 2, 3 positions that can accept, but you can put only 3 of the structures into that p orbital structure. What do you do with the 4th one? You got to get 4 attached in there somehow. Well, that's the dilemma, is that in the atomic valence, covalent bonding cannot occur in this configuration. So what has to happen is that this valence structure, which constitutes all of this part here, the second 2s and the 2p structures, has to undergo a change so that it accommodates the 4 incoming electrons to form the bond. And that is what we call hybridization. So that we are changing it. Now, the best way to look at this, and I found as far as an analogy in teaching this, when you have the structures drawn out in terms of the energy, we'll put a line here for energy, and we have, hypothetically, this is the 2s orbital right here, and it has the electrons in it right here, and then we'll put the 2p system up here. px, py, and pz, and we have 2 electrons there. Now I want you to think of it like this. Assume these are apples and oranges or grapes or whatever, and you throw them all in the blender. And so when you pour them in a blender and stir them up, you get, and then pour it out into 4 equal piles. Okay? So we have in the second energy level 1, 2, 3, 4 hybrid orbitals. Of course, this is done naturally by the molecule as it approaches the bond system. We'll explain as we go along. So we've taken the apples and oranges and blended them all together in a blender, and we've poured them out into 4 equal stacks. And each one of these stacks happens to have 1 electron in it. Now, there's no electron transfers, but the fact that we have 4 attachments in methane means that we need 4 hybrid orbitals. Each as a paramagnetic orbital. And so only in this configuration can you bring in your 4 s1 electrons into these 4 positions and generate a CH4 molecule. Now, we need to talk more about what is the specific nature and character of hybrid orbitals. So when we blend everything together and pour them out on the table in 4 equal stacks, the first thing you should notice is they all have the same shape. And that is, it's a kind of a asymmetrical figure 8. That is a hybrid orbital. All have same energy. So when you blend them together and pour them out, like in the second energy level, you notice I've drawn them all parallel to one another. And so all of these have the same energy. So you have 4 of these asymmetrical figure 8s up here. That have formed. Now, the orbitals can be empty, contain 1 electron, or a maximum of 2 electrons. So I can put at least 1 in there, or none, or max out with a diamagnetic like that. Of course, it is the electron orbital. As an electron orbital, whether it's paramagnetic, diamagnetic, or whatever, we assume it's negatively charged. So when we draw this, we kind of assume it's kind of a field of negative charge. In its hybridized state. Hybrid bonds connect at the apex. This is the apex of the hybrid bond, right there where it turns like that. So hybrid orbitals connect at apex and assume positions in space that minimize repulsion energy, as you've heard of before. So if we're talking about 4 hybrid orbitals, as we show 4 hybrid orbitals, then what you would have is a configuration that looks like a tetrahedron. So in the formation of the structure of methane, if it has 4 hybrid orbitals and they connect at the apex, so you take 4 of these little asymmetrical figure 8, turn loose after they connect at the apex, and they will naturally assume, when you have 4 hybrids, a tetrahedral geometry. Well, if you understand what I just said to that extent, then you'll understand that the next statement, all hybrids, or hybridization in all molecules is the same. A hybrid orbital in BeCl2 is the same as a hybrid orbital in H2O. So when you change molecules, you still have this asymmetrical geometry. So what we're talking about here, hybrids orbitals are the same in all molecular structures. It's just the number of hybrids that are involved in that structure. Or the structural geometry is defined by number of hybrids used in molecule. We got that. Now I'm going to expand this in a minute. Now, before I expand the number of hybrids into the geometries, I need to name the hybrid orbitals. Atomic suborbitals. Okay, we're talking about a set of hybrid orbitals that you define so many for a molecule. In CH4, we're using 4 hybrid orbitals. We had the energy of the p orbitals up here. 2 px, py, and pz. And then we had the 2s orbital that we're using. It was full, like that, energy. And we blended these two together, and we made what? In the second energy level, 4 equal energy structures. Each one looks the same, has the same energy, and they connect by the apex and form a tetrahedron. Now what I'm getting at is the name of the hybrids. While they're the same look, shape, energy, and everything in all molecules, when you're using when 4 hybrids evolve in the making of the molecule structure, you use how many of the orbitals are used. Well, you used everything here. It may seem that we're transferring an electron. That's really, in reality, is not what's happening. What you're doing is throwing all this in a blender, grinding it up, and pouring it out into 4 equal stacks. So what did we use? We took everything here. We took an S and 3 p orbitals, blended them together, and got all this. So the name is, for this orbital, is an sp3 hybrid orbital. And so you have 4 of them, and they're all called sp3s. It means simply that you are forming each one of these hybrid orbitals from an S, throwing an S and 3 p's into the blender and pouring them out in equal stacks. Because when we figure out how many hybrids we need, we use the VSEPR theory to say, okay, we need this many electron pairs, and that's the number of hybrids we'll need. And as I start using examples and applying this to molecular structures, you'll begin to see the pattern that I'm talking about here. But when you're working with these, you now have 4 paramagnetic hybrid orbitals. Each one's called an sp3. And it will assume positions in space that look like a tetrahedron. Right there. Now, having said this, then when we will use the VSEPR theory to define how many hybrids we need. So VSEPR analysis or theory gives us the number of hybrids needed. For a given molecular formula. Okay, and I'll show you how to do that. It's the same as we did yesterday. Valence minus substrate over 2 to get the free pair, and then the bonded pair. The sum of those is your hybrids, just like we did yesterday. If you have a molecule that has all of these are going to be binaries again, an AX2, What did we call that? That's a linear molecule. Okay? It uses two attachments on either side. Well, it uses two hybrids. And is made from an s orbital and a p orbital. So when you're talking about linears, you're talking about sp hybrid orbitals. Whatever else is there is irrelevant. And so when you look on back here and you're talking about linear structures, it is an AX2, and you have two hybrids, but you have two sp hybrids. So linear would be two hybrids called SPs, but these two hybrids, SPs, both are the same shapes, and they will hook up at the apex and assume a 180-degree bond angle, like this, and they will have the paramagnetic, and then whatever else comes in and bonds, hooks up to those hybrids, like that. Now, and you'll see how this evolves as we get deeper into this. So as you go down the list to AX2 being linear, so molecules that are linear will all use two hybrids, number of hybrids, and they all, the name, are sp hybrids. If you have an AX3, that gives you a trigonal planar geometry. Well, see the three, that's three hybrids in that one. And it takes an S and two P's, and it's called an sp2 hybrid. You can look on the handout that I gave you, and you can follow where I'm going here. And then you get the tetrahedral like we did with the methane. It has four hybrids in it, and it turns out to have four electron pairs by the valence bond there, the VSEPR. So that means any AX4, whether it has free pairs or not, is based upon a parent of a tetrahedron. And has four hybrids, and it's made from an S and three P's. Now, this sp hybrid looks just like the sp2 hybrid, which looks just like the sp3 hybrid. The only difference is the VSEPR says we needed four hybrids for this molecule, or whatever the VSEPR says for another molecule says if we have three, then we have three of these configurations, like that. And they all hook up and assume the same parent structures. And this also applies when you go above the octet rule. AX5, as you recall, is a trigonal bipyramid. And uses five hybrids. Now, if you run out of S's and P's, you go to the D's, and I'll show you that when we use the examples. And it uses one D orbital. So we have S, three P's, and a D. Add them up, five. It's five equal energy structures. Five of those hook up at the apex, and they make a trigonal bipyramid. And then, of course, the AX6 octahedral, or on octahedron, has six hybrids, AX6, and that's an sp3d2. We have to use two d orbitals. And again, there's an AX7 called a pentagonal bipyramid. Has seven hybrids, which is sp3d3 hybrid, and they all look alike, as you see on the handout that I've given you. So now we want to apply this idea to selective molecules and define the type of hybrid orbitals that will be used in defining geometry by the valence bond theory. Okay, so any questions so far? Everybody kind of follow me? Okay. So BeCl2 is our first structure. Now, use the valence shell electron pair repulsion theory to define the number of hybrids that you will need, and that's what you'll take from the central element. All right, what did I say? Okay, I said this. Vesper we have two things, bonded pairs and non-bonded pairs. Well, the bonded pairs have got to be two. That's because we got two attachments. Well, valence minus substrate over 2. Well, the valence is 2 times 7, 14, 15, 16. 2 berylliums in the second group. So 2 times 7 is 14 plus 2, 16. So there's your valence number. Your substrate number is either 8 or 2 times whatever the attachments are. Well, this is not hydrogen, so it's got to be 2 times 8, which is 16. Divided by 2, that's 0 over 2, and 0 non-bonded pair. So recall that the bonded pair plus non-bonded pair tells you the parent structure. So that's 2 plus 0 gives you a 2 for the parent, and it'll be linear, an AX2 parent. But here it also says that's how many hybrids you need from the central element. Everybody good so far in here? Okay. So at this point, you have to draw out the electron configuration like this. Beryllium being hydrogen, helium, lithium, beryllium, number 4 in the periodic table. Now remember, this is all occurring in the valence, so we'll just draw in the helium as the core because it's not going to change. Only the outer valence shell will change. So then we go to the second energy level, and what does it have in here? In beryllium, it has a diamagnetic paired electrons right there. Well, what does it say that how many hybrids do we need? Well, we have to take 2, we have to form 2 hybrids out of this. So what do? We throw this 2s orbital into the blender and pour it out in 2 equal stacks, just like we did with the S and 3Ps in the methane when we were working with it. So you just take the valence shell, whatever it is, throw it in the blender, and you get in the second energy level 2 equal stacks. Okay? Now, it turns out, let me show you one other thing here. Oh, I forgot the p orbitals. Px, Py, Pz. Now you need 2 hybrids. That's all you need. So you take an s orbital and a p orbital from the central elements, electron configuration, put that in the blender. And so what this is going to give you is in the second energy level, 2 equal energy, and it takes 1 s and 1 p to make each one of these, and you wind up with paramagnetics. Well, how do I know I have paramagnetics? Well, I don't have any non-bonded pairs to start with in the VSEPR, and I have to make accommodations for 2 attachments. And the only way you can bring in an attachment is have a paramagnetic looking for a paramagnetic, and then of course the chlorides are going to hook up in here, and 7 outer shell will fill up with these 2 right here. So now you're in this configuration. So you have two hybrid orbitals that hook up at the apex right here and assume positions in space, and those will go to this configuration with a 180-degree bond angle between the two, and each one has a paramagnetic electron. Now you can bring in the chlorides and put those in to complete the bond at the paramagnetic hybrids. Since you're using two hybrids, it would assume a position in space like we just defined, an AX2 geometry. Like that. Okay, to see how this is repetitive in making the analysis, in writing out how many hybrids you need and relating it to the VSEPR, we'll keep going and you'll see the repetition. Now, we can go through the VSEPR theory, and I can use the number of attachments, which is your bonded pair, and non-bonded pair will be 0 in this one. And so you have 3 bonded pairs and 0 non-bonded pairs. When you add these two together, you get 3 hybrids, as well as the number of electron pairs in the parent. So we take boron, has a helium core, and it has a 2s and 2p configuration like this. And it says I need 3 hybrids. So that's what I will take. I will take an S and 2 of the P's out of the configuration for the boron and make hybrids out of them. And I will use an S and 2 P's. That means each one of the hybrids that I form is called an sp2 hybrid. So this will go to, in second energy level, 3 sp2 hybrid orbitals. It said 3 hybrids. That's what we take. And so each one has to accommodate the incoming electron from hydrogen right here. Well, since you have 3 structures that look like this is what all the hybrids look like. Then they connect along the apex, and they will form a trigonal planar like this. And there's your central element, and your attachments, your hydrogens, will come in and hook up in those positions. And I'm keeping a secret from you that it's going to show up here in a few minutes. So what do we call this? Trigonal planar, based on an AX3 parent. Now, what happens if you have non-bonded pairs in it, like in the stannous chloride O2 thing? So we've already determined from the VSEPR theory that this has 2 bonded pairs and 1 non-bonded pairs, valence minus substrate over 2. So adding those 2 together gives me 3 hybrids needed. So that's what I'll take out of the central element. So we need to draw out the electron configuration for stannous or 10, and it's in row 5, series 5, has a krypton core, and we want to write out the configuration that emphasizes or shows the valence level, the highest principal quantum number, on the end of this configuration diagram. So as I write it out, I'm going to move all the lower energy orbitals to the inside and put only the valence out here, and move the valence to the outside and not worry about the Aufbau order. So we have a that's a 4D10. That's your transition row, and then you have a 5S2, and then 1, 2, and then a 5PXPYPZ110. So there's your configuration for Stannis. Now we're not interested in this, but we are interested in this, and we have to get 3 hybrids out of that. So that's what I will do, is I will take the 5S2 and the 5PX1 and the 5PY1, throw them in a blender and stir them up, pour them out in 3 hybrids. And it took an S and 2 P's. So again, while they are poured out and they look like this, they're called, still all of them are called SP2s, because I used an S and 2 P's in that. However, in here, when we make this in the 5th energy level, 1, 2, 3, and you have an unhybridized PZ over here, that says unhybridized PZ orbital. You didn't need it. So that's an SP2, SP2, and SP2. But we have to retain in there, we got 4 electrons here. One of these hybrids will maintain the non-bonded pair. And of course we have the attachments that we have to start with paramagnetics before we start hooking things up. And then of course the chlorides will come in and hook into those 2 positions. But we have 3 hybrids. So when you have 3 sp2 hybrids, it will give you a trigonoplanar geometry. Or parent, let's go with parents. But because one of these has a diamagnetic pair in it, when we draw out the configuration, one of those will have a non-bonded pair, and then you have 2 bonded pair, free pairs at the top, and then here and here, and then your chlorines will come in here. Like that. And so the results of this is the angle generated, as you see, between the bonded substrates only. And again, that is bent. So you have a bent geometry that is a result of sp3 hybridization, sp2 hybridization, sorry. 3 sp2s. Okay. Where I have drawn out some of the other types of configurations. See, here's the atomic configurations for the S and the 2 P's right here. And they blend together and they give you 4 sp3s. And that's what we're emphasizing here, is that you take what you need from the central element and make the hybrids based on how many you need. If you need an S and 1 P, you have 2 hybrids. If you need an S and if you need 3 hybrids, you take an S and 2 P's, and so forth. So ammonia we found has a non-bonded pair in it, and 3 attachments to the central element. It has 4 electron pairs. 3 bonded pairs, 1 non-bonded pair. So add those two together, we need 4 hybrids from the central element configuration. So nitrogen having a helium core, 2s, Z, px, py, pz, yeah, okay. Has that configuration. So this says we have to have 4 hybrids. So that's what we'll do out of this. We'll take an S and 3 P's and make 4 sp3 hybrids. Well, if you're working with sp3 hybrids, it always gives a tetrahedron. And so you can draw your little tetrahedron figure like that as the parent, with a nitrogen in the middle, but you have 3 hydrogens that are attached to that tetrahedron. And these are hybrid orbitals right here, as well as this one up here. But one of those hybrids has a non-bonded pair, sp3, 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 and you have to maintain that. You only need 3 attachments. That's what it here, and 1 non-bonded. So I'll put in one of the hybrids, I'll put that non-bonded pair up here. And then you have the 3 bonded pairs that accommodate the incoming hydrogens. And if you look at water, it does essentially the same thing, except it has 2 non-bonded pairs, which you put into those hybrid orbitals, and then 2 bonded pairs that accommodate the hydrogen. So we know that from the VSEPR theory, we have 2 bonded pairs and 2 non-bonded pairs in the VSEPR, which tells us we need 4 hybrids again. And of course that is 4 sp3 orbitals, hybrids. And that will give us a tetrahedral geometry, parent. But in that I have to have 2 bonded pairs and 2 non-bonded pairs. So starting with the tetrahedral parent and drawing it, there are my 4 hybrids right there. But I got to put 2 bonded pairs in that accommodate the hydrogens, but the other 2 bars in the tetrahedron are non-bonded pairs. Okay? So this kind of shows you the relationship between the VSEPR theory and the valence bond theory. Hopefully you're starting to see the patterns that are evolving here. Okay. So let's PCl5. So we'll start with the phosphorus configuration. And so when we look at phosphorus, it's in row 3. And so we have a neon core. And then we have a 3s orbital. And then we have the 3p orbitals, px, py, and pz. Paramagnetic, and then, diamagnetic, paramagnetic. So there's your valence shell for phosphorus. So we found, using the VSEPR theory, 5 bonded pairs and 0 non-bonded pairs, which says I have to have 5 hybrids. So I need to take those, but I've got an S3Ps. Where did I get the other one? It's out here, the 3D. Remember, D has 5 orientations. I'm going to call them D1, D2, D3, D4, and D5 just for illustrations. So in order to accommodate 5 chlorides, I have to take 5 parts, suborbitals out of the valence. So that's an S, 3 Ps, and a D. And we'll disregard this portion down here. We don't need it. And so what do I have? This will give me in the third energy level 1, 2, 3, 4, 5 hybrid orbitals that are called sp3d1 orbitals. And so you have 5 of them. Now, people would typically publish, if they use this, 5 parentheses sp3d1s, like that. It's just a shorthand note. You won't see people drawing everything out like this. So, what do I have no bonded pair, no non-bonded pairs. So everything in here is paramagnetic. So I put an electron in. And so now we're able to accommodate all 5 chlorides in what we call a trigonal bipyramid geometry. Remember the lazy triangles, and draw it like this, then vertical line like that, and from the center element you go to the points of your geometries. And so we have paramagnetic all the way around, and then the chlorides will come in and attach and form the bonded pairs like that. So we have a parent, AX5 parent, equal to the geometry. Geometry and parent are the same. Okay? Does it have a non-bonded pair in it or not? Well, if you apply the VSEPR, yes. It has 4 bonded pairs and 1 non-bonded pairs. Add them together, and that means you will need 5 hybrids from the central element sulfur. So we write out sulfur, and is in third row, and that would be a neon core, and it has this as an atomic configuration in the valence structure. But remember, the d orbitals are out here, but they're empty. And so if I need 5 hybrids, I'll have to include that d orbital in my blender. So using 5, 1, 2, 3, 4, 5 sp3d1 hybrids. And since one of the hybrids has to be a non-bonded pair, I'll go ahead and put it here, and then everything else is paramagnetic. Well, only the first one is diamagnetic. So since I'm using 5 hybrids, which is 5 sp3d1s, I'll have an AX5345 parent, which is a trigonal bipyramid. So I want to draw out that trigonal bipyramid. lazy triangle, then a vertical, and another vertical straight down, and then draw radials out from the center. But in this structure, where do I put the first, well, here it is, first non-bonded pair, above and below or in the plane? Remember what I told you? Anybody?
In the blank.
In the plane. So I'll just pick a position in here, and everything else is bonded pairs like that. And we see in this the geometry is based upon this right here, and we see that as a seesaw. You see that's the seesaw geometry in there. From the side perspective, you have your fluoride, fluoride, you have a non-bonded pair, fluoride, and fluoride. It looks like a seesaw in that diagram. Those are AX5 parents with SP3D1 hybrids. Okay, I'm getting that. So see if you can turn those into the hybrids using the techniques I just showed you. Next one moves into the octet parent SF6. Let's see who else we've got in this collection. IF5 and XEF4. And so all of these are an AX6 parent like that. And you remember electrons enter above and below plane when you're putting the electron pairs in, the non-bonded pairs in, whereas they first went into the triangle in the trigonal bipyramid. So let's do SF6, which has 6 bonded pairs and 0 non-bonded pairs, and ultimately that's 6 hybrids needed. So we'll use 2 d orbitals in this one. So it'd be an sp3d2, and those will go into the octahedral configuration. So sulfur, which has a neon core, 3s, 3 px, py, pz, and 3 ds, and we just take 1 and 2 in the configuration. And those d orbitals are empty for the present. But since we need 6 hybrids, that's what we'll take. We'll take an s, 3 p's, and 2 d's. And this will give me 6 hybrid orbitals, 6 sp3d2 hybrids. Now, since we have 0 non-bonded pairs, what do we put in the blanks? We put paramagnetics only. And each one is called an sp3d2 hybrid. They hook together and they form an octahedron. Now, drawing the octahedron, remember I said draw a lazy square, then put your verticals here, and from the center radiate out to the points like this, okay? And then you enter your substrates, and there everything is saturated, i.e. bonded. You don't have any non-bonded pairs. Now if we did IF5, you have 1 non-bonded pair, And so you could draw the same thing and put iodine in the middle and may say put the non-bonded pair, say below or above the plane, and it'd be a square pyramid. This is octahedral, which is defined by the SP3D2s. This one's square pyramid is also defined by an SP3D2, but just happens to have a non-bonded pair in it. And XEF4 has 4 bonded pairs and 2 non-bonded. And so those are called square pyramids. Square planar, sorry. You can look on the handout that I gave you on the names of those, but once you fill these two at the top and the bottom, the only thing that's left is a square plane. This is right down here. That's the only thing left. And so you need to work on that so you can pick them out on the exam day. Now, up to this point, I have defined hybrid orbitals and related those to geometries, in that all the hybrids look alike in shapes and what have you, and they assume positions in space that minimize repulsion intervals. However, that's all they do, is they define the geometry, but they in themselves are not chemical bonds. There are only 2 kinds of chemical bonds. The 2 kinds of chemical bonds are formed when these substrates come in and attach one another. And the 2 types of bonds are called sigma bonds and pi bonds. A sigma bond the symbol looks like an O with a flag on the top of it, like that. Has a line of symmetry between the bonding nuclei. This means that you can draw a line through the center of both nuclei in that particular bond. If you have hydrogen bonded to hydrogen, then you have a structure with a nucleus overlapping the orbitals, your bonded pair here. And so if I draw a line through that moves through both nuclei, then that's what we call a line of symmetry between the nuclei. And if that condition is met, then the bond here is a sigma bond between those. So that's all. That's the main thing. The hybrid just supports the electron pair or non-bonded pair to accommodate incoming substrates. So like in methane, CH4, we see a geometry that looks like this with hydrogen, 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 and hydrogen, central element carbon. Now we could take a ruler, if you wanted to, and draw a line of symmetry through the carbon in each of the hydrogens that have attached by covalent bonds, like that. So here we have 4 sigma bonds in that structure. Now you have what this sigma, each of these sigma bonds is a result of. is sp3 and an s orbital. Of course, the s comes from the hydrogen. So what you're essentially talking about is a hybrid orbital and then a spherical from the s orbital, and they will overlap to form that diamagnetic bond. And then, of course, you'd have the other nucleus over here. And and then if you check the symmetry, you'd find that a line would go through both nuclei, and that would, an sp3 bonded to an s is a sigma bond. So that's what the nature of this is. You only have two kinds. I'm fixing to show you the other kind. In some structures, you have orbitals that do not undergo hybridization, but yet contribute to the bonding in that molecule. Ethylene is a structure, if you draw out the Avio-Beck, the Lewis dot structure on this, you'll find, I like to draw it like this, it has a double bond in it, like that. Well, how do you account for the bonding from hybrids in a structure like this? Well, you recall from the VSEPR, the structure at each carbon in this case is an AX3, because see, remember, we take and assume that multiple bond is a single bond, and the attachments, and there are three attachments in there. So when I have an AX3 or three substrates, that means I have to have three hybrids from carbon. Well, when you draw out carbon and look at its electron configuration, you're full in the 2s, and then you have paramagnetics in the px, py, and empty in that one. But it says I only need three hybrids, so that's exactly what I take. And one of the hybrids on the end down there remains unhybridized and takes part in the other part of the multiple bond in here. It's called an unhybridized p orbital. Again, we still throw everything in the blender. Well, we throw three of them in the blender and leave one untouched, but it still accommodates another electron in there. So what happens is carbon valence turns into this. Because we need three hybrids, that's an AX3. And AX3s are associated with what? sp2. So we have an S and two P's, and then a P hanging out there, a PZ hanging out that didn't do anything. So this would be, I'd write it the other way, 2, and then a 2PZ unhybridized, but it's going to carry one electron. You might even, if you want to, promote out there, because that has to accommodate part of the multiple bond, and I'll show you in a second. But here you have the paramagnetics, and this is an sp2, sp2, sp2. Now, this is an AX3 geometry for this structure. Let me come up here. So if I have a carbon right here, I'll have this trigonal planar right there. And this is an sp2, an sp2, and an sp2, because that's what the VSEPR said I needed. However, I cannot ignore this 2pz, so it's still attached. You remember p orbital, and it has an electron in it. And this is an unhybridized p orbital sitting there. Well, in the ethylene, you got two centers. This is carbon 1, and then you'll have carbon 2. It does the same thing. It has an unhybridized p orbital like this. You'll have sp2, sp2, and an sp2. Now these have paramagnetics, and of course these will accommodate the incoming hydrogens. Each one of those has a paramagnetic, and they bond. Now, the hydrogens and this sp2 overlap in here will hook up. Those will all be sigma bonds. So when I connect the hydrogens, I'll have a sigma, an sp2s. This will be sp2s overlap, which gives us a sigma, two sigma bonds right there. And this one will be an S and an sp2 overlap, and it'll be another two sigma bonds. sp2 overlapping sp2 is another one. You have 5 sigma bonds in there. Now, what happens to the unhybridized p orbital? It overlaps, the lobes overlap and form the second kind of bond, and it's called the pi bond, and it's only found in double bond, triple bond configurations. And a pi bond is a side, by definition, sideways overlap of unhybridized p orbitals. From two different centers. And when it's completed, what you have is a cloud above and a cloud below the plane of symmetry of the molecule itself. It takes 2 lobes to make one p orbital. One pi orbital, not p orbital. Pi bond. So a pi bond is the sideways overlap of unhybridized p orbitals. Now the rest of the structure is all sigma bonds because they have those lines of symmetry. So this ethylene has 5 sigma and 1 pi bond structure in it. So, using some of these graphics, you'll see here's the center, the planar between the 2 carbons. Some of them will rotate, and some of them it'll have a rotation around that center sometimes. But at any rate, looking at this one down here, we still have that unhybridized p orbitals in here, and as a result these will interact right here and do this and form that cloud above and below, and these 2 lobes that are showing here are the pi bond. And another way to look at that is here. So you have your carbons and your carbons here, and then you have your top lobe and the 2p hybrids, 2p unhybridized, making the pi bond above and below that plane. But when you apply the names of the bonds, those are pi bonds, one pi bond for the two lobes, and then you have a sigma, 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 and sigma, like that, because those have lines of symmetry in them. If you look at your handout at the bottom, here is an example of a triple bond, acetylene. Now, it's a little difficult to see this, and I thought I had another plate, but you have two pi unhybridized pi p orbitals forming two pi bonds. Like, let me show you this. One of these is a sigma, but the other in there is a pi bond. But when you go to acetylene, like this, you have two pi bonds, and then you have one sigma between the carbons, and of course those are sigmas and sigmas. So you have three sigmas and two pi bonds in acetylene. Well, I can expand that a little bit for you. C2H2. So what we're doing is we're taking two carbons and hooking them together. So taking carbon with a helium core and 2s, 2xyz, px, py, pz, and that one's empty. When you do the Vesper, you find out that, or the Avio-Beck if you want to, this has 3, 4, 5 covalent bonds. But the outcome of that is you have between the carbons in here and the hydrogens, you have 3 sigma bonds and 2 pi bonds. Well, these 2 pi bonds are a result from 2 unhybridized p orbitals. So 2 of these orbitals in here, 2 of the orbitals will not be hybridized, and 2 will hybridize, and in the second energy level you'll have an sp, sp, and then also the py and pz, like this. That, and then of course your core, and that's your carbon. But these hybrids right here will form a linear structure. There's your carbon, but it also has 2 unhybridized p orbitals. So this is an sp and this is sp, which accommodates the hydrogen coming in and forms a sigma. But this one also has another sp over here for the second carbon, and then 2 unhybridized p orbitals on the second carbon also. On this second carbon, I should have drawn the structure somewhere. So if you have 2 hybrids, 2 pi bonds in it, you have to have 2 different centers, each one containing 2 unhybridized, these 2 unhybridized p orbitals. Then you have an overlap above and below in the vertical, and then behind and in the front. And so when this is all said and done, hydrogen overlaps, the SPs overlap. This is an SPS overlap, this is an SP S overlap, giving a sigma. This gives a sigma. The one in the middle here is an SP-SP overlap, and that's also a sigma. So you have 3 sigma bonds. But when you take into account the sideways overlap of the these orbitals, like I showed you in the diagram here a minute ago, these will sideways above and below. Also, you have them in and out of the plane. Kind of hard to see sometimes. But that will create a cloud up here and a cloud down here, and then one in and out of the plane of the structure. So those 2 lobes make a pi bond, and then those 2 make a pi bond. So you have 2 pi, I know that's a mess, but you have 2 pi bonds, and then you have 3 sigmas, 1, 2, 3 in there. So that accounts for the acetylene. Well, that's the only 2 kinds of issues you'll run into. For example, if you had a complex molecule, something of this nature, how many pi bonds and how many sigma bonds do you have in that structure? Well, all of the multiple bonds have at least 1 pi bond. If you had a triple bond, you'd have 2 pi bonds. That's the only options that exist. So you have here a pi bond, here a pi bond, and there a pi bond. So in that entire structure, you only have 3 pi bonds. Everything else in here has a line of symmetry through it and is a sigma bond. One, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 sigma bonds and 3 pi bonds in that structure. Now the issue is pi bonds are incredibly high reactive character. In other words, they expose the electrons very much into the reactive field. That is, if you have a carbon bonded to a carbon with 2 clouds above, that's a very strong negative charge. So anything floating along that's positively charged will interact with that very rapidly. It's a very strong and very rapid interaction, and add into that structural portion of that molecule. So that's why it's important to understand the nature and identification of the type of bonds. Pi bonds are have an incredibly high degree of reactivity. The sigma bond does not necessarily have that high reactivity unless there's a high separation in electronegative differences. Okay, for double bonds, no matter where, no matter what, do it like this. You always have a sigma and 1 pi. 1 sigma, and the other one is a pi bond. If you have a triple bond, no matter where it is, now I'm just talking about between the carbons now, not out here. Okay. This has, I can do this neatly. I just took 2 bars and said that's 2 pi bonds, whereas the one in the middle, just hypothetically, you can choose any one you want, in there is a sigma, 1 sigma bond. So you can say the triple bonds have 2 pi's, 1 sigma between the elements. Double bonds have 1 pi and 1 sigma between the elements. Always.
Okay, so going back to the last structure that you drew, why would there be 9 pi bonds and not 12
No.
pi bonds? Or, I'm sorry, 9 sigma bonds and
Okay,
not
see, these are
12?
line of symmetries. 1, 2, 3, 4. See, you only find the way I did this is you only find the pi's in the multiple bonds
Okay.
in the discussion as far as the rules. And so 1, 2, 3 pi bonds. So we throw those in. But in each double bond, there's at least one sigma bond. Did I not put the sigma? The other's a sigma. I
No.
probably forgot that one. Okay, and
One
then
more.
the other one is a sigma bond. Okay, thank you.
Okay.
So I guess I need to add 1, 2, 3 more sigmas now until I have 12. Yeah, I was just looking at outside the double bonds. Okay, yeah, thank you. But yeah, that would give you 12 sigma bonds. And as far as the structural identity, then the only thing beyond what I've given you up to here is try to remember as you go forward into newer courses, if you take the next level, a pi bond is highly reactive and is adapted to substitution. So if you, like, again, if I had some kind of hundreds of positive fragments you can stick in there, and if you put it in with this molecule, it's going to stick to one of those carbons somewhere in there. So that's just the nature of it. Now, the course will tell you who does what, the organic course anyway. But all I want you to understand is how to say, okay, this has got a double bond, it's 1 pi, 1 sigma. Or triple bond is 2 pi's, 1 sigma. And then you go from there.